Hello, can you hear me?
Yep.
Thank you. Good afternoon, everyone. I'm here to talk about my research journey in researching and building an IoT network security solution. A little bit about myself. I'm an application security consultant / software developer at Datacom in the cybersecurity team. I'm based in Auckland. I'm lucky to be here. I love computer science. I'm enthusiastic about all areas of the field, especially programming, security, data communications, and data science. And this talk kind of encompasses a little bit of each of those fields. So why am I giving this talk? Back in 2020, when COVID version 1 first dropped, I was a postgrad student looking for a thesis topic for my master's. And my research interests at the time revolved especially around the detection of cyber attacks, specifically by how network intrusion detection systems worked, how they were able to observe traffic patterns in the network and then identify attacks from that. So specifically, I want to learn about the mechanisms of that, like how it was achieved, what insights I could find to further improve the accuracy of those systems. Moreover, in recent times, the application of machine learning techniques in this domain, especially in traditional computer networks, is quite a rich body of work. So I was also wanting to apply it to a new area, and something that also caught my eye was the integration of IoT devices for automating building operations in commercial settings, specifically like smart buildings or industrial IoT, which exposes traditionally isolated systems to the internet, which is obviously a huge security concern. So I want to merge these topics, and I came up with a problem space of a lightweight intrusion detection system for IoT-based smart buildings or large-scale IoT networks. This is just a really broad overview of the smart building stack, right? So you have your IoT layer, which will be connected through the IoT gateway to the network, which will be sending its sensory information to the cloud or cloud tools like smart building tools to perform like smart data analytics on, or applications such as energy management to effectively manage the building's operations. Remote control as well, if you want to turn devices off at certain times, so on and so forth, things like that, as well as security monitoring. So with that in mind, the integration of these IoT devices into this environment, what is some of the threat models that I was looking to detect was specifically around volumetric DDoS attacks. So IoT devices are generally easy targets for attackers due to their lack of security design. While individually these devices have limited computational capabilities, exploiting a large volume of them can be an effective tool for launching a volumetric amplification attack. So this has led to the rise of IoT botnet malware such as Murthy, Hajime, and Bashlight, which specifically target these devices to launch DDoS attacks against like a target server. So a smart building network, therefore, is a really lucrative target for attackers who exploit. This is just another overview of a reflective amplification attack. For example, a DNS amplification attack. An attacker will have a botnet of devices, and your IoT nodes could be one of those devices that have been compromised by Murthy or Hajime. And the attacker will instruct the bots to initiate an attack against the target server. These bots will then send DNS requests spoofing the IP source address of the target server, so requesting on behalf of the target server and send it to the DNS server. And the DNS server will then respond to the request with an increased response size compared to that of the request, therefore amplifying the traffic size and reflecting it to the target server and flooding its network pipe essentially. And that's how the DDoS attack is carried out by exploiting existing network traffic protocol vulnerabilities that are quite hard to defend against for the target server. So how to detect if the IoT devices on my network are being exploited to launch a DDoS attack? Obviously, if you have a smart building network with hundreds to thousands of IoT devices in your building, you want to ensure that the devices are being used in the way that they're authorized to do so. You don't want their processing to be used to launch DDoS attacks against someone that's obviously a violation of their authorization, right? So you want to detect these incidents so you're aware of it and to gain visibility into their operations as well. There are multiple detection techniques to do this. There are host-based intrusion detection systems as well as network-based. Host-based operate on the individual nodes in the network and monitor system log files to identify patterns exhibited by viruses at the operating system level. The issue with this is that IoT devices are resource constrained, and therefore this is not a scalable solution for a large amount of nodes in your smart building network. Network-based intrusion detection systems monitor and analyze network traffic from a single sensor point to identify malicious traffic. This can be implemented at a centralized controller and avoids using the device's resources, so it wouldn't use an IoT device's resources. The issue with this is there's highly variable traffic in the network, which makes it hard to accurately identify attacks. So there'll be a high false positive rate because attack traffic will blend in with benign traffic and it'll be hard to tell which is which. So that's why you have a high false positive rate. Within network intrusion detection systems, there's signature-based and anomaly-based approaches. Signature-based approaches rely on a known database of attack signatures to identify the attacks, which means that if it's a novel type of attack, then it won't be detected, and you have to constantly keep this database of signatures up to date. Whereas anomaly-based approaches learn the normal behavior of traffic in the network to identify variations that represent attacks. Traditionally, in typical computer networks, this is also quite hard, and that's why you have high false positive rates because of the high variability of traffic. But IoT networks and machine learning algorithms this is where the application of machine learning techniques for IoT networks hold some promise, because IoT devices have really predictable patterns. They communicate with a small set of endpoints and limited capabilities, which means they have limited traffic flow types. Therefore, you can train your machine learning model to learn these normal traffic patterns and then detect anomalies which should represent attacks, essentially. So, given this problem space, so how would you go about designing the traffic classification system for a large-scale IoT network? Well, first of all, there's a few more challenges. First, primarily, which is IoT networks have a wide range of devices such as cameras, lights, switches, sensors, so on and so forth, which have a diverse range of network traffic patterns within themselves as well. For example, if you think about it intuitively, if you're streaming your IoT device camera and its video feed to your phone, comparing that to a feature that will allow you to take a photo of the feed and see it through your phone, the traffic patterns are completely different with those two different activities, as well as comparing that with a switch, IoT switch, which just has two states, which is just on and off. And the traffic patterns between those two devices are quite different, even though the device itself is predictable. So there's the challenge of, because you're monitoring from a single sensor point, you have high variability of traffic between these two types of nodes as well. There's also the challenge of devices of the same type, such as cameras, which are manufactured from different vendors, also exhibit different network characteristics due to the difference in the network protocol stack implementations. So if you use UDP to stream or TCP to stream, that also has an impact on the input and output of traffic into that device. However, a good center point to where we monitor all the nodes in the network is a network middle box, such as a router or an SDN switch, because all the traffic in the network is traversed through this node. Moreover, the routers are computationally limited, which imposes more constraints on the complexity of the techniques you use for anomaly detection. So having said all this, the desired characteristics of the traffic classification system, therefore, should be scalable. The detection pipeline must be efficient to scale to hundreds to thousands of nodes. It should address the variability of traffic across the nodes in the network, as well as handle the addition or deletion of nodes to the network, because you might be replacing new devices or adding ones or removing them. So the network structure might change, so you should be able to handle that as well. Modeling the normal traffic patterns using lightweight features. Machine learning models, supervised or unsupervised, learn on the combination of traffic attributes, packet level or flow level, to characterize the network traffic patterns of devices. So you need to characterize the traffic patterns in the network through a set of attributes that effectively capture their patterns using low-cost features. We have different types of features. Flow-based features essentially capture how packets are sent, and they incur less computational costs compared to packet-based features, which goes into inspecting what is in an individual packet. And deep packet inspection is a more time-intensive process, so it's a little bit harder to scale for a large amount of nodes in your network. So the optimal solution, therefore, balances the trade-off between scalability and accuracy well. So we come to the solution design of, so modern research suggests that dedicating a classification model for each node in your network is able to achieve high accuracy, because the variability of normal traffic patterns of the classification model learns is then limited to that node itself, as well as it allows the handling of addition and deletion of nodes. So you will be able to just train that model for that node itself. You can then leverage the predictable nature of the IoT device's traffic to extract a small set of flow-based features by coarse-graining the flows at the source device, which I'll go into a little bit later on. So you extract a small number of features per device and train the model on those features. We will use a lightweight clustering algorithm as opposed to a more computationally intensive machine learning technique such as neural networks, because we're trying to limit the complexity of the solution. So how did I go about implementing and testing all of this? Luckily, the researchers at University of New South Wales at Sydney open sourced their IoT traffic data from their testbed above. You can see that it includes a whole variety of devices, from cameras to lights and switches, and all sorts of IoT devices. The dataset also includes benign traffic to train the models on to learn the normal traffic behavior, and then a mix of benign and attack traffic to test those classification models on. The dataset also contains DDoS attacks, both direct at the device itself, as well as the reflective ones that I've mentioned earlier. And there are varying rates of the attacks. So there's 1 packet per second attacks, 10 packets per second, and 100 packets per second attacks as well. It's quite a large data set, has over 80 PCAP files for you to pass, and this is just an overview of that. So the detection pipeline essentially is just the traffic capture files. You pass them, you group the packets by device and by time, you extract features based on that grouping, and you classify it. That's the overall process. And I implemented this in Python. This is just a large overview where you'll be passing the packets, serializing the data, and feeding it into your machine learning pipeline, which trains and then tests the models. So in the feature extraction process, something to optimize what the model learns on, the features that the model learns, is made more effective by limiting the number of flows that you extract features on. So because, again, IoT devices have predictable patterns, how can we leverage this? Well, we can group their traffic. And I grouped it by the location and direction that a flow is from. So whether the IoT device is talking to a device on the local network, then the location is a local, and whether it is sending the traffic or whether it is receiving the traffic. So by using this filter, you essentially get 4 coarse-grained flows with internet inputs, internet outputs, local inputs, and local outputs. And then you extract features over the packets grouped by time as well. So you use a sliding window and sampling rate algorithm. So this is, again, a data science technique that you use for training your machine learning models, where you use a sampling rate and then you use a larger sliding window over the sampling rate to extract features from. So as you can see here, I've used a sampling rate of 30 seconds in these brackets, and then a sliding window of 120 seconds. So there's 4 smaller brackets where you will see how many packets are there and what are the size of those packets. And then you're extracting features like what is the mean size of packets, or what is the mean number of packets, what is the standard deviation of bytes and packets over those smaller windows, what is the total count. So those are really simple features that you can extract. They're not computationally intensive compared to more complex features such as like the the derivatives of packet interval times and things. There's a lot more complex features, but this is a lot more simple. So you can train your model on these features, and you input this into your clustering algorithm. But also, I just want to quickly show the coarse grading of flows and extracting these features, such as standard deviation and mean, produces a unique traffic fingerprint. You can see that the devices all have different fingerprints, like the traffic kind of clusters uniquely. And this, I just want to highlight the difference between 2 cameras as well, where the patterns are quite different, and they use different protocol stacks as well. I think one of them uses UDP and the other one uses TCP, if I remember correctly. But essentially, devices of the same type also have different fingerprints. And if we were to just, instead of filtering on location and direction, if we don't filter at all, if we just apply that same data sampling technique on all the traffic at the node, then you can see that when we plot it over standard deviation and mean in the x-axis, then we can see that there's unique fingerprints for the devices in the network, and it clusters quite well. So we use those features and we plug it into the clustering algorithm. So why do we use a clustering algorithm? One, K-means clustering algorithm is quite lightweight, and also it clusters the data points in a spherical shape. This means that we can use the spherical shape to set a cluster boundary, and then use the data points that are outside of that cluster boundary and classify them as anomalies. And those classifications are what your clustering algorithm is then saying is your malicious behavior or your attacks. So that's an inherent inherent downside of anomaly detection, as you can see, is you will always have some false positive rate. So even when you set the cluster boundary, you will have some outliers. Just the final point is just wanted to show that using those features, the probability, this is the CDF plot of a device of the features, the probability of the benign traffic and the attack traffic, how you can see that it's clearly the features are quite different between benign and between separate attack traffic rates. You can see that it exhibits a really consistent pattern in all of the flows. Yeah, that's a bit. Oh, sorry, I concluded that totally wrong. Conclusion: IoT network security solutions is a growing field with the integration of IoT into critical systems. Solutions that provide visibility into the network operations is key to managing risk. And the code of all of this, such as the graphs and everything, is all available on GitHub if you want to go check it out. That's how I ended.
My bad.